There is only one perfect solution. There are clues that will try to trick our team.
Hello there, everyone. My name is Crazy Caleb, and today we are taking a look at one that has been highly requested: multicolored switches. So what we're going to do, and just to let you guys know, the reason why it took so long to make this is because this module was actually bugged for a little while, and it was just a series of unfortunate events, really. Just gonna make sure I'm recording. Yes, I am. So it was a series of unfortunate events. It took a while, and I'm sorry about that. But today is finally the day we can get this done. So let's get some terminology straight. First off, before we even start this up, this has to do with many different color combinations in the form of red, green, and blue. For those of you who have practiced this kind of color combination with either Color Edition or Simon Says, this should be pretty good for you. For those of you who don't know this, I would highly recommend getting used to how this chart works, because this is essentially what this module is based off of, and we will have to be converting these back into the red, green, and blue states, as they are referred to. So what we're going to do is, how this module works is, first let's gather our information here. But first we need to get a little bit of terminology cleared up. So you will always have 4 sets. What exactly are the 4 sets? Taking a look here, it's cycling through 2 different states, where the LED here in the middle is on and off. The 4 sets will correspond to the top row on whether it's both on and off, and the bottom row whether it's on or off. Those are your 4 different sets. And the 3 different states that we're about to go through, red, green, and blue, those will be on each of the sets. Each set will always have 3 states. So what I'm going to do is, for each color in these LEDs, we're going to be decomposing the LED colors into primary color components, red, green, and blue. And each row of the 5 LEDs will create a set, like so. So before we even do that, there is a specific order because of how this module wants you to gather. It's not off of this table, trust me. And it's based off of in reading order, with the first set being the lit LED on. So we were going to gather this information as top LED on, and then top LED off, top row off, top row on, top row off, bottom row on, bottom row off. So let's do that. So top on. Our colors on top on are white, red, green, white, and I believe that was a magenta. Yes. And that's our top on. Top off, in this case. Top off is a magenta, blue, red, green, and I believe that was a white. Yes. Bottom on, and let's pull up Notepad here, because I'm actually going to use a lot of space here. So bottom on. Wait for it to cycle back. Magenta, white, black, and yellow. Bottom off is going to be a black, magenta, cyan, red, green. Let's space that. Alright, so now we have gathered our 4 different sets, as I said here. Top on, top off, bottom on, and bottom off. The top and the bottom referring to the rows, and the on and off referring to the state of the LED in the middle. So now what I'm going to do is, for each of the 4 sets, as it says down here, we are going to break these apart and decompose them into the red, green, and blue states. So what I'm going to do is, the dots will correspond to not present in the color, and the red will just correspond to its present. So in this case, red is present in this one, that one, and not that one, and this one, and this one. Like I said, I am going to go through this pretty fast, so I would expect you to know your red, green, and blue color mixtures. Red, green goes into yellow, red, blue goes into magenta, green, blue goes into cyan, and all of them combined is white. So next up, green. Green is green, dot, green, green, dot. Next up is blue. Blue, dot, dot, blue, blue. And that's that set. Next up, let's do the next one. We have red, dot, red, dot, red. Next up, green, dot, 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 green, green, and blue, 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 dot, dot, blue. Next up, red, 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 dot, red. Next up, green. Green is dot, green, green, dot, green. Make sure I'm recording. I'm sorry, I really don't want to make sure that I'm not recording because that would suck right now. And blue is blue, 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 dot, dot. And for our final set, dot, red, dot, red, dot. Green is dot, dot, green, dot, green. And for blue, dot, a blue, blue, dot, dot. And just like that, we have our color combinations figured out. So now what we're going to do is we're going to take a separate step here. So the reason why this has been such a highly requested module for me to do is because the manual is kind of worded a little bit weirdly. So what we're going to do first is we need to find the correct set of which the module is in, whether it being top on, top off, bottom on, and bottom off. This is just for the set, so that'll give us 3 options to work with in this case. So in this case, as you can see, the switches are also colored in red, green, and blue mixtures. So let's break the switches apart. So in this case, we have switches, yellow, magenta, white, magenta, red, breaking that apart. And I'm not going to do it the same way I did before. I'm just going to count how many times red is present, green is present, and blue is present, not the specific location. So red is present 1, 2, 3, 4, 5 times. Green is present 1, 2, 2 times. And blue is present 3 times. Okay, so now that we figured out how many times it's present, we needed to count the number of red, green, and blue coloring in all the switches, which we did right here. So we need to then find the color with the minimum and the other color with the maximum amount of coloring. So in this case, our minimum value is a 2, so green is our minimum value, and red has a 5, which means it's our maximum value. And now, let's just cross off these numbers. These numbers are completely irrelevant after this point. If there were 2 colors that shared the same max and min value, we would take the first one of this order, red, green, and blue. Else, if all are equal, then take red as both as both your minimum and maximum color, which we didn't have to worry about in this case, so we're good. So now, we're going to find the 2 states. The 2 states, remember, 2 states meaning these specific color decomposures. Find the 2 states with the corresponding color that have more or less lit LEDs based on the color you found. What exactly does this statement mean? So of the colors we found up here, we're going to find the state with the least amount of greens present, and we're going to find the state with the most amount of reds present. So in this case, we have, let's take a look for our greens. First, we have 3 greens. We have 2 greens, 3, and 2. There are 2 values. Now, what exactly do we do with this in this situation? So it will be in reading order of how you will determine which state could be possibly considered. So in this case, this is our first one in reading order, including top off. So this is going to be our minimum value. So now let's find red with our maximum value. So the most amount of red, 4, 3, 4, and 2. Now, this happens to be another situation where we have 2 values that are worth 4, which are our most values. So this one is in reading order, top on, so we are going to mark that as our maximum. And that's what you need to do for that step. Now, we're gonna observe the parities between one another. So we have 4 reds present here, and we have 2 greens present here. If they both share a parity, then the solved and ignored states must be in the set that has the minimum one. parity. What exactly does that mean? Parity means if they both share a parity, which means that they're both odd or even. They're both even in this case. So, they both do share a parity. The states of the solved and ignored must be in the set that has the minimum value. Minimum value right here. So this set right here, these three states correspond to the set that we're going to be looking for. That's just breaking it down right there. The solved state can be in one of these three states. We have now determined which area we're in, so let's actually find the correct solved and ignored states. So now we're going to do the same thing, counting the number of red, green, and blue coloring, except we're going to do it for the sockets. The sockets are the little sort of balls inside of here, or the round shapes, spheres, whichever you prefer to call it. I really don't care. But counting those, we're going to do the same thing we did for right here. So I'm going to do it like this. Red, green, and blue. So we have 4 reds. We have 5 greens. And we have 0 blues. So finding the color with the minimum and maximum of the amounts here. So blue is our minimum because there's 0. And green is our maximum. We're going to get rid of these numbers because those are irrelevant now. And the state with the chosen minimum color will be the solved state, and the state with the chosen maximum color will be the ignored state. The other states are wrong with no exception. So, as it says here, the chosen state with our minimum color is going to be the solved state. So of this set right here, of this top offset, blue is going to be our solved state, and green is going to be our ignored state. And the rest of the module, rest of the color decomposers, is going to be wrong states, which we have to avoid. So now what we need to do is, what do these actually mean? So the colors that are present on this specific decomposer, they mean up. So what this state is actually saying is we need to get the switches to the position to 1, 2, and 5 being up. While avoiding the rest of the positions, we can ignore that 4 and 5 are not present. So, taking a look here. So blue. So now, how exactly do we get to this? So we need to figure out how to get to this. Can we have all of them down? I'm looking for literally a ... Can we have all of them down based off of these other wrong states of which we must avoid? So I'm just going to list them out for personal reasons, just to kind of visualize it a little bit better, hopefully. So we need to avoid up, 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 down, up. We need to avoid down, up, up, down, up. We need to avoid up, 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 down, down. We need to avoid down, up, down, up, down. Down, down, up, down, up. We need to avoid down, up, up, down, down. And for these other ones up here, we said we ignored this state, so that doesn't matter. So we need to also avoid up, down, up, down, up. Up, down, down, up, up. Up, down, up, down. And up, down, up. So we need to figure out how we're going to get here, because this is definitely a tricky one. So can we flip down 4? Yes, we can, because there's no down, 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 down state. Nothing happens, we're doing good so far. Can we perhaps get 5 up by itself? I'm sorry, these are not helping me at all, so I'm just going to get rid of them, or not even worry about them. Can we have just 5 up? I'm not seeing anything that's preventing me from getting 5 up. Can we have a 1, 5 up? Perhaps. Let's try that. Let's take a look. 1, 5. I am not seeing a 1-5 present, however I'm going to make sure. So let's flip 1 up. And just like that, we have 1 up. And now we are 1 move away from our solve state, so that automatically means that we can just flip the second state up, and that should solve the module. And just like that, it did. Now, probably a lot of you are thinking like, holy crap, that's a lot of work. But trust me, after a while, it really does get easier. So, some of you are also probably wondering, like, hey, what the heck, why didn't you use this table down here? That is for another case, one of which I actually want to cover right now. So, what would happen if we had to use the table here? So, how exactly do we use the table? If the sockets were all equal to one another, if the counting in the sockets were all equal to one another, then that's where we would use the table. How exactly do we use said table? So let's take a look back at our example here. So we said that we would find it at top off, and our corresponding minimum value of top off was green. So this was our determining our correct set. As I would mark it. So now, if all were equal, then the chosen LED state in the last step will give you the solved and ignored states. So we found our state at top off green. And this is from the last step of the switches. So we found at the correct set. If they both share parity, we said the minimum one. This was our minimum one right here, as green was our minimum. So what we would do is look at the top off set for green. So the unlit top set of green. And these are the numbers that we would use. The chosen LED state in the last step will give you your solved and ignored states. Find it in the table and take that number's position in the table in reading order. So in this case, our solved state would be the lit top set of blue, and our ignored would be the lit bottom set of green. And that's how that works. But that's only if the red, green, and blue coloring of the sockets all equal one another, all have the same value. And that's how that would work. And then we just do the same thing. So now let's do another example, because this is definitely a tricky one to understand, and I hope you guys really understand this, because it took me a bit to understand this as well. So let's grab our top on, top off, bottom on, and our bottom off. That's a semicolon. That's a semicolon again. So for our top on set, we have blue, yellow, red, blue, green. Blue, yellow, red, blue, green. Our top offset is a yellow, blue, magenta, green, cyan. I'm just going to confirm that. A yellow, blue, magenta, green, cyan. Our bottom on set is a red, magenta, yellow, cyan, yellow. Red, magenta, yellow, cyan, yellow. And a bottom off is going to be blue, magenta, red. Wait for that to come back around. Yellow, white. And I'm just going to confirm that I have every single value right. Blue, yellow, red, blue, green. Yellow, blue, magenta, green, cyan. Green, cyan. Red, magenta, yellow, cyan, yellow. And blue, magenta, red, yellow, white. Okay. So now that we have all of our information present, let's do the color decompositions again. So red is going to be dot, red, red, dot, dot. Green is going to be dot, green, dot, dot, green. And blue is going to be a blue, dot, dot, blue, dot. Okay. Next one. Red is going to be red, dot, red, dot, dot. Green is going to be green, dot, dot, green, green. And blue is going to be dot, blue, blue, dot, blue. red is going to be red, 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 dot, red. Green is going to be dot, dot, green, green, green. And blue is going to be dot, blue, dot, blue, dot. And finally, for our bottom off state is going to be a dot. Red, 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 red. Our green state is going to be, dot, 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 green, green. And blue is going to be blue, blue, dot, dot, blue. Excuse me. Okay, so we've got our color decompositions all prepped up. So now, let's take a look at our switches. We have red, black, white, red, white. Red is present in 3 of them. 4, actually, excuse me. Green is present in 2. And blue is present in 2. Get rid of you. And in the meantime, let's also count our sockets, because I'm here. So red, green, blue. Our sockets are red, blue, white, yellow, and black. So red is present in 3. Green is present in 2. And a blue is present in 2. We were very close to what is called the edge case, as I have demonstrated there. So, let's find the correct set. Our maximum for the switches is 4. This is the switches. Suck. Let's break them apart. So the maximum is 4, and however, 2 of the colors share the same value. So we are going to use this little list right here, red, green, and blue. So green pops up first in that list, so this is going to be our minimum value. So let's get rid of these numbers because those are irrelevant now. So let's find the minimum amount of green. We have 2, 3, 3, and a 2. This one pops up first in reading order instead of the bottom off, so this is our minimum right here. Our maximum is red. 2, 2, 4, 4. This one pops up in reading order first. Lit always tops the off. So this is our max. So we have 4 here, 4 reds, and we have 2 greens. So they both do share a parity, so our solve state is going to be in this one right here. And this is irrelevant. So now what we need to do is, hey Def, we need to take a look at which of the following set states our module, our solve state is going to be in. Let's use the switches, or the sockets, excuse me. This is clearly our max, and we're going to use the same order, red, green, and blue, to determine our minimum, because they have 2 of the same values. So in this case, this is also our minimum. So, like it said here, the chosen state with the minimum color will be the solve state, green will be our solve state, and the maximum will be our ignored state. So now what we need to do is we need to figure out how to get 2 and 5 up, while avoiding the wrong states as well. So now let's ask us the question. This could be really straightforward, or this can be really complicated. Let's try and get just 2 up. Will that work? I really haven't actually seen any values with 1 up in them, so I believe we can put up 2. Like so, that did work. And now let's put up 5 because we're 1 away. And just like that is the module. Let's take a look at one final one, because I hope you guys are really understanding this. So now, top on, top off. Bottom on, and bottom off. You know, just put bot. Alright. Okay, so our top on is going to be a cyan yellow, magenta cyan yellow. Just going to confirm that, cyan yellow, magenta cyan yellow. Top off is a black, green, yellow, green, white. Bottom on is going to be a blue, blue, cyan, yellow, black. And bottom off is going to be magenta, green, magenta, cyan, white. I'm going to confirm that. Yes. Alright, let's do our color decomposition. Dot, red, red, dot, red. Green, green, dot, green, green. And blue, blue, dot, blue, blue, dot. Alright, next up, red, dot, dot, red, dot, red, dot, green, 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 and blue is, dot, 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 blue. Red is dot, 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 red, dot, green is dot, dot, green, green, dot, and blue is blue, 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 dot, dot. And for our last one, red is red, dot, red, dot, red. Green is dot, green, green, and blue is blue, dot, blue, blue, blue. And just like that, we have our color composition, decompositions. Alright, so for our switches, red, green, and blue. So, for our switches, we have 0 red. We have 0 red. For our greens, we have 1, 2 greens. And for our blue, we have 1, 2. So red is our minimum, and just like that, these two share a value, red, green, and blue. First one on the list is green, so green is our max. Let's find those states which has the minimum amount of reds and the maximum amount of blues. Okay, so let's find the minimum amount of reds. Right here, this is our minimum, no doubt, because we have 3, 2, 1, 3. So this is our minimum. And green, let's find our maximum amount of greens. We have 4, 4, 2, 3. This one comes first, as we've said here, top on. So this is our max. So we have 4 in this specific state, and we have 1 here. They both don't share a parity. They're both not even or odd. So the set will be in the maximum one now. So this is going to be our set that we're looking for. So in this specific set, what is going to be our solved and ignored states? So our sockets, let's check. Red, green, and blue. We have 1 red, 1 green, no, 2 greens, excuse me, and 2 blues as well. This is our minimum, as we said, and green, blue, like always. Green is going to be our max. So, now, let's get rid of the numbers, like I said. And the chosen minimum color will be our solved state of this specific set. So red is our solve, and green is our ignore. Okay, so now what we need to do is we need to get to 2, 3, and 5 being up, while ignoring the rest of the, while trying to avoid the rest of the states as they are wrong. So let's try and get 1 down. Does 4, 5 work as a position? It seems to work fine. Okay. Can we perhaps get a 4 down? This is corresponding to just 4 being up, so we can't put 5 down. Actually, we don't want to, so... no, we cannot have just 5 up. This is a wrong state, and just to prove you so...
Not it, I'm afraid.
That would be wrong, because this is a wrong state, and it doesn't flip. If you press it, it doesn't flip with you. It's not going to cooperate with you, so we have to find another way. So let's try and get 2 up, perhaps. So wait, 2, 4, and 5. Let's see if that's anywhere on here. 2, 4, and 5. That is present. So let's try and get a 3, 4, and 5. Anything that really gets us close to the solved state. 3, 4, 5. Is that perhaps present? 3, 4, 5. That has a 1, so that doesn't matter. So I think we can put up 3. That's right. So next up, let's try and put down 4. No, immediately. No, we can already tell that that's not going to work. And we can't put up 2, so that's not going to work either, because of also right here. So this is definitely one of the trickier situations I've been in. So let's try and put up 1 perhaps. So we have 1, 3, 4, 5. But no, this is the position down here too. So we're going to have to get a little bit creative with how we work with this. As this probably isn't going to work. So we maybe just need to find a different way. So, because if we put any switches up, let's try and just figure out if we can actually put any switches up or down. 1, no, because that's present. 2, no, because of that state. 3. Well, we just came from putting 3 down, so we don't want to put that up unless we absolutely have to. 4, 3, 5, can we have that? No, we cannot, right there. And just 5, no, because that's present. So, this is actually not going to work for us. So we're going to have to put you back down and find a different way. Like I said, this can be a little bit tricky. You can get lucky or you can't get lucky, so it's just making sure that you pay attention and you don't run into a wrong state. So, let's try and take a look here. Can we try and put 2, 4, and 5 up? No, we already agreed that we couldn't because 2, 4, and 5 is right here. So let's try and get maybe 1 up. Because we can get to this state perhaps, since that's our ignored state. And we can work with that. So let's see if 1 works. 1, 4, and 5. Which I'm not seeing anywhere. Actually, that brings us back to our original state. So now we can get 2 up because this is an ignored state. So 2 works, like it said, it's an ignored state. So now let's try and get all 5 of them up. And then work backwards from there. Can we get all 5 of them up? Yes, we can. I'm not seeing any 5s anywhere. Okay. So now we need to get 1 and 4 down. Let's try and see if we can find a position that works with us. Can 1 go down? No, 1 cannot go down because of this state. So let's try 4. Can we have a 1, 2, 3, and 5 up? That seems to work. Let's put down 4. Just like that, it did work, and we are 1 away from our solved state, so that automatically means we can put down 1. And just like that is a solved module. Thank you so much, ladies and gentlemen. I really did enjoy this module. It's a really fun one, once you understand it. The manual is a little confusing at first, I must admit, but to be fair, it was the module creator's first module. As always, thank you guys for watching. Stay crazy, stay cool, and I'll see you guys later. Bye-bye.